Hello, everybody. This is Professor Ma, and this is the sections on work. We are going to do another applications of fundamental theorem of calculus by adding a bunch of little pieces of things and to change that into integral. And in particular, the things we're going to add up are what in physics we call works. So the place we start with how we define works in a very simple way. Okay, so we define works as force times distance it travels, and one of the easiest way to think of about force is gravitational force. So like the force of the weight of a book, and so suppose of a book that's 10 pounds. And I want to pick it up and lift it up 5 foot. Then we have a calculation of how much work is done, how much work is required. It's 5 foot 10 pounds or 50 foot pound. Okay, so. And what we want to do now is suppose imagine we, instead of having a book that's 10 pounds, suppose we are holding a bucket of waters, and we are lifting the bucket of waters straight up. But at the same time, there's a pipe connected to the waters, and the water can be, the pipe is putting waters into the bucket, so the bucket could be heavier, or the pipe could be sucking water out of it. So the weight of the water changes as I lift the buckets up. Now, that's what we wish to calculate. So this basically can, in other words, basically can think of the framework of this type of problems in these bucket problems, right? Picking waters going up, and the bucket waters changes. Okay, in terms of its weight. Okay, in particular, one type of force that's that we know the rules of the how much force it is in relation to spring. Oh, by the way, the relation to spring and the force as it stretches is a linear formula. Gravitational force between large body is a second degree force. Okay, so let's go back to the spring. Okay, in the case of spring, we can think of in terms of the bucket of waters analogies, is that there's a pipe is coming in, and the water as we lift this bucket up, the water actually getting more and more water, so it's getting heavier, and the pipe is pumping the water constantly. So the force as it goes up, weight gets increased constantly. Okay, so and this is exactly this how the spring works. In the picture over here, I draw it upside down. Okay, basically, we say almost relaxed positions. Okay, and I stretch it. And now there's a force goes against, want to pull it back, contract to the original relaxed positions, okay? And that force, according to Hooke's law, it depends on, it's proportional the distance you stretch from the relaxed position, okay? And it's a constant times the distance you stretch. The further you stretch, the force for the contraction is greater, okay? And it's directly proportional to the constant, to the distance, okay? And that constant depends on what kind of spring it is. Some springs really tight, really hard to pull. But some springs is loose. Slinky is really loose. It's really easy to pull. Okay, so, but the spring, we obey this law. So each spring has a spring constant. And here's the examples. A bungee cord stretch from a relaxed position and it stretched 5 feet longer. Okay, and it holds 15 pounds of weight. Okay, and it got stretched by 15 pounds of weight. So what's the spring constant? Putting the distance and 15 into the formula. So okay, then the constant is 3 pounds per foot. It means for every foot you want to stretch, you need to add a 3 pound weight. Okay, and so find the tensions when it is stretched 25 feet. Also, when it's 25 feet, and the weight, the force pulling back is going to be 25.375. Okay. In other words, if you put a 75-pound weight, then the bungee cord is stretched 25 feet. Now, we're going to do this on a spring. We're going to pull the spring from, maybe the spring's already been stretched. We want to stretch the spring further, longer from point A to point B. Okay, it's like we want to remember the buckets of waters. We want to lift it from x equal to A up to x equal to B. At the same time, the bucket itself is getting heavier and heavier. How do we calculate that the total amount of water? It's not same weight anymore. Well, we cut it up into little pieces. Cut what up? Okay, we'll cut the distance up, right? So from point A to point B, we partition. Okay. And we say regular partitions, so they all the same size. And let's let delta x to be the distance from one number to the next numbers. Okay. And now suppose now this spring have stretched to the point xi minus 1. Okay. So at this point, the tension with the force on the spring is going to be K times xi minus 1, right? That's Hooke's law, proportional to the distance from the relaxed positions, which is xi minus 1. Now, I want to move that by a distance of delta x to the next point, so multiply time the distance delta x. Okay. That little piece of work, I call it delta W if you like, okay, which is the force times the distance. Okay, so this I should call delta W in particular the small amount of work I need to do to make it progress from I minus 1 point I. Okay, for this particular expression. Now, I'm going to run this through starting from x equal to 0 up to, okay, so we have this formula. This is adding all the amounts, all the little piece of works. Okay, now I'm going to let delta x go to 0. And that is a summation turns into a integrations by fundamental thing in calculus. So integrate from A to B on this member stretch from the point A to point B, and force times the distance. Okay, and this, if you like, is dW. These little things is the, if you like, this is what we call the work differentials, the little pieces of work required. Okay, so this part, the integral of dW is W, summed up all the little works, is the total amount of work. Okay. Here I'll let you read this one particular is about a spring. You have to find out, we find out the spring constants. Then he asks you how much work is done to stretch this particular spring from what? From 4 to 20 feet. Okay, and then it's integrated and it's done. In particular, the application we're going to use is to calculate amount of work to pump liquids in a solid. Okay, the solid will be a very regular shape to on top to some surface, some point on top of the solid to pump it up. Okay, now this is different from taking the entire solid, lift entire things up to that destinations. This is in terms of thinking of this, like think of pumping. Okay, I have a pump on top of the surface is sucking up water over to the top. So in other words, I'm pumping the things from the top layer by layer over to some destinations on top. Okay, not lifting the entire tank, just lift it up. Okay, it's pumping layer by layer. Okay, and then of course we want to calculate how much work it will take. Okay, so here's the situation, and we're going to use water tank. Okay, and in general, you will see in the book that you see simple rules for the densities of you pumping something else. You're pumping oil, and then you need to know how much work you need you pump to be able to do, right? But here we pump waters. Okay. And that's a density of water. That's just a constant. Okay. And in this case, I'm going to set x starting from the top of the solid. Then b is the bottom of solid. So I'm taking my measuring tape. Okay, pump 0 down to bottom. Okay. This is arbitrary. In fact, I'm going to change this later. Okay. But we get a formula from this first. So suppose this x direction going down, and there's some arbitrary x somewhere in the middle. We're going to call this x, okay? And I have a cross-sectional area. Suppose I can get a cross-sectional area of the solid of the container, okay? Then let me partition this x-axis into regular partitions, and a of x, xi, and the cross-sectional area is a of xi. I multiply that by delta x. Delta x, of course, is this between the distance between here is delta x all over. Okay, delta x, the layers of delta x, the layers of waters, each one thickness delta x. Okay, at xi level with the cross-sectional area a xi times delta xi, and that will be a slab of waters sits right below at xi level. Okay, and that slab of waters, so volume, it's approximately, it's like a cylinder, is the area AXI times the delta of x, okay? And that, I know the weight of this. It's going to, weight of this slab of water is going to be the density times the volume, okay? This is the volume, approximate volume. Very important. This is approximate delta V, and how much volume times the density is how much weight. And I'm going to take that and I'm going to lift it all the way up. In this case, how far does it have to go? It has to go the distance from xi all the way up there. Okay, how much is that? That's h plus xi. Okay. So again, the weight of that slice is that formula. And the distance it will travel is that much. Hence, just for this individual slice, think of that as a book now. That slab, think the weight is rho times this, all this weight, that's how much you weigh. I'm going to move it up h plus xi. So times h plus xi, and that's it going to be the works required for that particular slice. Okay, that's just for that slice. But now I'm going to add up all the slices, 1, 2, 3, 4. So I get all this weight and all these works that require. Writing a summation notation. Okay, and let me review one more time. A of x is the cross-sectional area. Dx is how thick it is. I really should write them together because multiply them is the volume of the slice. That times the distance it travels. Okay. And I take delta x go to 0, and that is in the integral. Okay. And the rho can move out as constants, and then move ax to the side. Okay. And so I get this nice formula of total amount of works that's required to pump this entire body of solids of waters over to the top. Okay. Couple of, okay. Notice this part basically is the volume of the slab. And this part really goes with the rho. Rho times dV is how much you weight. So basically, it's a distance times how much you weigh, and adding that together. So this is the total. You know, this is the this is the weight. Okay, this is the work. Oh, I should have used the same W. So let me now mention. Another thing I have to point out, these formulas only apply when I set my x over here, starting 0. Okay, but I could set original x from here equal to 0. Okay, and then in this case, all the way to the bottom will be h plus how much is it? B. Okay, right, here's h, is down below is b, and the solid will start at a point where h is. Then the integral will be h to h plus b. And the x will only appear somewhere in here that it has some area formula, right? A of x. That in this case, and times dx is the dv times the rho. And then finally multiply this by x. That's the distance they travel. Okay. If I were to set x equal to 0 on top. So again, how this formula work depends on where you measure your tape measure from. Okay, from all the way from the top, or from top of the solid, or from the top of the, or maybe from the bottom up. They all work. Okay, so in general, this is the formula. So we're going to do two different cases. Okay, and we're going to look at the cross-sectional area first. What kind of things we can control cross-sectional area? First one, cylinder, a drum. Okay. So if I set my ruler going from top 0 to bottom, then AX is going to be pi r squares, the cross-section. How about semisphere? What about cross-sectional area? Where do you want to point the X from? Or if I point X again from center to bottom down, then the going down the depth of X, then the radius is the black line is going to be big R squared minus X squared. And then the crossing sectional area is pi R squared, pi times big R minus X squared. So these are how cross-sectional area are calculated. So here's an example how we pump waters out of a semisphere, 10-foot over the rim. So in other words, okay, and so there's a curve over, and then so the one just over the other side. So there's a pump. Okay. And in this case, I think I set my x from 0 from the surface down to the top. Okay, so now I'm going to use that formula. Cross-sectional area is pi 100 minus x squared. Okay. Multiply times dx times rho. Is that how heavy it is? Okay. And now I need to move these slides how far? X, right? This is a depth x. So I want to move times the distance x. That's the works needed to these particular slides. And that I integrated from 0 to 10. Add them from 0 to 10. We need to integrate. Okay. And we'll put the dx on the side. And then you just get a number. This is one cross section we will use a lot. That is this cross section of circle or sphere. Okay, and the other place we'll take cross section is a cone. And these are very basic geometry. In this case of sphere, we use Pythagorean theorem. In the case of cone, we're going to use a proportional triangle to get the radius of the circle. Okay. And these two shapes we'll use quite often to extract cross section. Okay, one's Pythagorean theorem, and here's is the one that uses similar triangles. Okay, and this one, I just let you read it. Okay, basically to get the radius, you just use a very simple formulas and proportional triangles to get the radius of this r. Okay. G equal to x, so this is the air cross-sectional area, and that's and how far does it have to travel? It have to travel 18 minus x, because this is x is from here to here. Okay, again, I mean, this one x, this case x I set it from here to here, so here's x. So from here to here, we compare to here to x, and this is a cross-sectional surface. It has to travel 18 minus x because this whole trip is 18. Let me find bottom of time. Okay, so then the rest is calculated. Okay, and that's it. I'll work. Okay, and pumping water. Bye bye. Until next time. Bye bye.